Good morning, students. We'll start with the today's class. In the previous class, we have solved a few numericals and we have seen what is steady state error and error constant. Just to recall, I will brief you out, right? Okay. With respect, whenever the input is unit step, then unit ramp, then unit parabolic, right? So unit step is associated with the position error constant, and unit ramp, that is velocity error constant. Then parabolic, it is acceleration error constant. Then Kp is given by limit, just I am recalling what we have studied in the previous class, limit limit s tending towards 0 into g of s. This will give me the position error constant. Then velocity error constant Kv is given by limit s tending towards 0, s into g of s. These all things are very important and it's required for us. So just I am recalling s into g of s. Then if I want acceleration error constant, limit s tending towards 0, s square into g of s. Just observe here. Just it is g of s here, s into g of s, s square into g of s. Based on the kind of input what we are applying, unit step input, unit ramp and unit parabolic, and corresponding error constant, position error constant, velocity error constant and acceleration error constant. And what is steady state error? Let me write it here. I don't have space here. Let me write it here. Steady state error. So ESS, steady state error, whenever the input is unit step, we got it as 1 divided by 1 plus Kp, if you remember, right? Similarly, for unit ramp, the steady state error was 1 by Kv. Sorry, 1 by Kv. 1 by Kv. So here the steady state error is 1 by Kp. Sorry, Ka. Sorry, 1 by Ka. Right? So corresponding steady state error. What is Kp we got? Kp is K we got, system gain. Kp equal to K. Here also Kv equal to K. K equal to K we got. They all depend on the system gain K. We have found out. Right? The next, today we'll see the types of control system and the steady state errors associated with them. We'll see. Then the dominant poles of the transfer function. This concept also we'll understand at the last. And we'll solve few numericals also. Right? We'll see. The next, types of control system. Yes, already you will be knowing we can classify the system, control system into several classification, that is based on automatic and feedback, open loop and closed loop. Then several classification we have seen, but based on the location of poles at the origin, so you can classify the system as type 0, type 1, type 2, and so on and so on. So how this classification works out, already just I will brief you out. Just you can take the S plane here. So S plane is a complex plane, sigma j omega, right? So you can observe at the origin, this is the origin, right? At the origin, none of the pole is located. So that I will call it as, if none of the pole is located at the origin, I will call it as type 0 system. Suppose if one of the pole is located like this at the origin, then I will call it as type 1 system. If there are two poles lying at the origin, means I will overlap. Two poles are lying at the origin, then I will call it as type 2 system. If there are three poles at the origin, I will call it as type 3 system, and so on, right? Based on the number of poles lying at the origin in the S plane, right? For the given open loop transfer function, if the poles are lying at the origin, based on the location of the poles at the origin, we can classify it as type 0, type 1, type 2 and type 3 and so on, right? Okay. This classification already we know. Just okay, with the other perspective we will see here. The open loop transfer function g of s of a unity feedback system can be expressed in two ways. One is standard time constant form, and another one is pole 0 form, right? Suppose the given transfer function g of s is equal to k into 1 plus t1s, 1 plus t2s, 1 plus t3s and so on, divided by s power n into 1 plus t1s into 1 plus t2s and so on. Just in order to differentiate numerator and denominator, just we will add, instead of just simply calling t1 of s, we will call it as tz1 of s, tz2 of s. Here in the denominator, tp1 of s, tp2 of s and so on, right? Because the numerator terms will give me the zeros, the denominator terms will give me poles. So suitable, notations we have to use, right? And k is called the system gain, and this s power 1 n will tell us the type of the system, because if n equal to 0, n can take 0, 1, 2 and so on, right? S power 0, S power, if S power 0 means only 1, nothing, that S term is not there, means it is type 0 system, because none of the poles are lying at the origin. If it is S power 1, means n is 1, means one of the pole is lying at the origin of the S plane, I will call it as type 1 system. If it is S square, two poles are lying at the origin, I will call it as type 2 system. If it is S cube, type 3 system and so on, right? So this term in the denominator will judge, it is dominating, which will judge what type of system it is, right? We'll see. So if I express in this form, I'll call it as time constant form. Another pole zero form, how to write the same open loop transfer function in pole zero form. G of s is equal to k dash, it is system gain. In order to differentiate, k and k dash one and the same, right? So we'll try to relate k dash system gain s plus z1, s plus z2 and so on, in the form of factors we have written here, right? Divided by s power n as it is, s plus p1, s plus p2 in the form of factors. The numerator terms will give me open loop zeros, the denominator term will give me the open loop poles, right? So I can express the open loop transfer function either in standard time constant form or pole zero form. But most of the times we will be using the transfer function in time constant form only, right? Okay. Then how this k and k dash? K is in time constant form, k dash in pole zero form. How they are related? You can observe here. K is equal to k dash into the product of the zeros, z1 into means I, zi means I ranging from 1 to 2, pj, j running from 1 to 2 and so on. So here if you take you can take z1 common here, z2 common here, z3. In the denominator you can take p1 common, p2 common. So it is product of all the zeros in the numerator, z1 into z2 into z3 and so on, divided by the product of the poles p1 into p2 into p3 into and so on, right? So that is the relationship that exists between k and k dash. K is equal to k dash into the product of the zeros z1 z2 divided by the product of the poles p1 p2 and so on, right? Okay. And we have to give significance to this denominator term s power n in the time constant form, right? In both the equations, whether you take standard time constant form or pole zero form, it corresponds to the number of integrations in the system. Yes, if n is 0, I told it is type 0 system. If n is 1, it is type 1 system. If n is 2, it is type 2 system and so on. Also, it corresponds to the number of integrations in the system. For example, if you take Laplace transform, if I take differentiation d by dt of f of t, right? How I will write s into f of s. Is it fine? Then if it is Laplace transform of d square by dt square of f of t, then I will write s square into f of s. If it is differentiation, you know it, right? If it is Laplace transform d cube by dt cube f of t, means s cube into f of s. If it is different integration, then I will write it. You can observe here Laplace transform of integration of f of t into dt, for example. Then I will write what I will write, f of s divided by s. Is it fine? There is one integration. If there is double integration, f of t into d of t, then I will write it as f of s divided by s square. If it is triple integration, I will write it as f of s divided by s cube and so on, right? So if it is differentiation, the s term will come in the numerator. If it is integration, it is coming in the denominator. S square, s cube, it continues. So this is coming in the denominator, s power 0, s power 1, s power 2 and so on. So this s power n term in the time constant form of the open loop transfer function indicates the number of integrations. Type 0 system means no integration. No integration. Type 1 system means one integration is involved. Type 2 system, it has two integration and so on, right? Based on the power of n, right? The number of poles located at the origin, we can classify the system as type 0, type 1, and it corresponds to the number of integrations in the system, right? And one more thing, as s tends to 0, means the denominator term, as s tends to 0, this term dominates in determining the steady state error, right? So based on this s power n, if it tends to 0, then this is very much important in determining the steady state error of the system. Means whether the system will achieve the steady state or final value or not, that we'll see next, right? Okay, already I told the classification based on the number of poles lying at the origin of the S plane, or also number of integrations. So if n is 0 in the denominator, right? If n is 0, s power n, then there is no integration, because no integration is known, and one of the pole is lying at the origin. So none of the poles are lying at the origin of the S plane. If n is 1, yes, one integration is involved in the system and one pole is lying at the origin of the S plane. If n is equal to 2, I will call it as type 2 system and two integrations are involved and there are two poles lying at the origin of the S plane and so on. This continues. Already I have told in the previous slide itself, right? Okay. I hope it is clear. Type 0 system, type 1, type 2. If it is type 0 means no integration and no poles are lying at the origin. If it is type 1, one integration is involved in the system and one of the pole is located at the origin of the S plane. Type 2, two integrations are involved and two poles are lying at the origin of the S plane. Just I have summarized it. Then next we will see the steady state error. Types of control system we have seen based on the location of the poles or number of integrations, right? Then next we will see the steady state error associated with the types of control system, type 0 system, type 1, type 2. What are the steady state errors that are associated with type 0 system, type 1 system and type 2 system? We'll see, right? We'll not go for type 3, type 4, right? We'll restrict our study for type 0, type 1, type 2. Okay, we'll see for type 0 system. For type 0 system, what is g of s? Observe here. This is the general time constant form. G of s is equal to k into 1 plus tz1s 1 plus tz2s divided by s power n. If it is type 0 system means n is 0. What is s power 0? It is 1. So this will become 1. This will vanish. 1 into 1 plus. So we will write here. So s power n is 1 here. So it is not shown here. S power n. I hope you understood, right? So hence this is type 0 system because n is 0. So s power n. S power 0 it is 1. In the denominator term 1 will be coming here, right? So I will not write this. So this is the open loop transfer function in standard time constant form. Standard time constant form. Okay, next we'll try to find out the steady state errors. That is position error constant, velocity error constant and acceleration error constant and corresponding steady state errors. ESS, ESS, ESS. We'll find out one by one. What is this KP? We know that the position error constant whenever the input for the system is unit step, right? So limit s tending towards 0, g of s. Is it fine? So limit s tending to what is g of s? This is g of s, right? So limit s tending towards 0, g of s. Substitute s equal to 0 everywhere. This s0 is right. So I am left out with only k. So kp is equal to k we got. Kp is equal to k. Means the position error constant depends on the system gain k, right? Then what is steady state error associated with this? We'll see whenever the input is unit step, right? Whenever the input is unit step. So I will mention here, right? So what is steady state error, right? With respect to that is we call it as position error, right? Steady state position error, ESS. So 1 divided by 1 plus Kp. This we know already, right? Already I have listed out. I have briefed you also in the first slide, right? 1 by Kb, 1 by Ka, right? So 1 divided by 1 by Kp. What is Kp? Kp is equal to K here, right? So substitute here 1 by 1 plus K. That is equal to, this is some finite value I will get. We can observe here. If the output tracks the input, then the steady state error should be 0. But I am getting some steady state error is involved here, right? And that is finite value. If I want to eliminate that steady state error, what I should do, I want to decrease this steady state error. I want to make this steady state error 0. What I should do, I should increase the system gain K. Go on increasing the system gain K so that the steady state error goes on decreasing. But there is limitation. I cannot just keep on increasing this value of K or system gain, right? This particular system gain. I cannot just keep on increasing it, right? There is limitation for that. So to some extent, I can go on increasing the value of K or system gain so that the error gets reduced. I hope you understood this, right? For this type 0 system. Next, whenever the input is unit ramp, right? So we'll at that time we'll find out the error constant, velocity error constant kv, and we know that velocity error constant is limit s tending towards 0, s into g of s. So limit s tending to 0, s into what is this g of s? G of s is this one. Substitute here, right? Okay. Then substitute s equal to 0. If I substitute s equal to 0, here it is 0 and every 0 into this entire term, it will be 0 only. So we got velocity error kb is 0. We got kb equal to 0 here. So what is the steady state error? So with respect to velocity, right? ESS of velocity is equal to 1 by kv. This we know. What is kv? We got it as 0. 1 by 0 is infinity. So the steady state error is ESS what we got here. In this case, it is infinity in this case. right? Here in this case we got finite value ESS. Then next, whenever the input is unit parabolic, so there exists the acceleration error constant Ka, and it is given by s tending towards 0 s square into g of s. S square as it is, this g of s substitute here, so it is substituted here. Substitute s equal to 0, so that 0 into this entire term will vanish, so I will be getting acceleration constant Ka equal to 0. Then we know that the steady state error ESS of acceleration is 1 by Ka. What is Ka? We got it as 0, substitute here, 1 by 0 is infinity. Means once again we got the steady state error is infinity, right? So finally I can say that for a type 0 system, right? So the steady state error is having finite value only with respect to unit step input. Whenever I apply the unit ramp or unit parabolic, the steady state error is infinity in both the cases. So I should not apply the unit ramp signal and unit parabolic signal for the type 0 system, because the steady state error will be infinite. Actually the steady state error should be 0, right? Because whenever the steady state error is 0 means the system has attained the steady state value or final value without any error, means there is no difference between the desired output and the actual output. But if I apply the input as unit ramp or unit parabolic, I am getting the steady state error as infinity, right? Steady state error as infinity. So I should avoid these kind of inputs, unit ramp signal and unit parabolic signal for type 0 system, right? But I can apply the unit step input. But here in this case the steady state error is not 0, I am getting some finite value. It depends on the system gain, 1 divided by 1 plus k. It depends on the system gain, right? If I increase the system gain, I can decrease this steady state error. I hope you are getting, right? So the same analysis we will see for type 1 system and type 2 system. For type 0 we have seen. Similarly next we will see for type 1 and type 2 system. Okay, these two sentences you read it out, the same thing has been already told by me, right? Okay, the next, if let me make you understand here. So suppose for type 0 system, if the input is unit step, I am getting the steady state error is finite value 1 divided by 1 plus k. So let me, this is 1 divided by 1 plus k, let me make it 1 divided by, suppose it is first order system, it will slowly rise and it will try to reach the steady state value, but there is a difference between the actual output and the desired output. This is nothing but our steady state error, and it is 1 divided by 1 plus k. If I want to make it 0, I cannot make it 0, but if I want to reduce the steady state error, means the system has to finally achieve the steady state at time t equal to infinity, right? So go on increasing the value of k system gain so that this steady state error reduces in case of first order system. If I come to the second order system here in figure B, so the steady state error is 1 divided by 1 plus k. It is having damped sinusoidal oscillations, and you can see there is a difference between the desired output and the actual output. This is steady state error, right? I hope you understood. So go on increasing the value of k so that the steady state error reduces, or else, right? I hope you are getting in case of both first order system and second order system, right? The next we'll try to make the same analysis of steady state error with respect to type 1 system. What is type 1 system? Observe here. Yes, okay, this is standard time constant form, you know it, standard time constant form, standard time constant for, right? So g of s divided k into 1 plus this, you know. But observe here, s power 1, so s power n in the denominator, this term, right? I am concentrating on this term. So s power n is 1 here because it is type 1 system, so s power 1, it is nothing but s, so we have written s here. I hope you are getting, this is type 1 system and other terms are as it is. Then whenever the input is unit step, so find out the position constant, position error constant, limit s tending g of s, apply this is g of s, substitute here, this is g of s, right? So it is written here. So substitute s equal to 0, it is coming in the anything divided by 0, right? 1 by 0, right? So this, so anything divided by 0 is infinity, so I am getting infinity, means kp I am getting it as infinity, kp is infinity. Then what about the steady state error? So we know this steady state error is 1 divided by 1 plus kp. What is kp? It is infinity. Anything divided by infinity is 0. So the steady state error what I am getting is 0 here. Yes, this is what is desired, right? So steady state error should be 0, means I can apply unit step input for type 1 system, then no problem. Next, if it is unit ramp, Find out the velocity error constant, limit s tending to s into g of s, s into this is s into this is the entire thing is g of s, right? This is the entire thing is g of s, s into g of s. So s will get cancelled, substitute s equal to 0 here, so I am left out only with k, so I am getting k. So velocity error constant is k, it depends on the system gain k. Then we know the steady state error ESS, right? So it is 1 by kV. What is kV? kV is equal to k, we got it. So substitute here, so it is 1 by k, means I am getting some finite value. So here the steady state error is some finite value, and it is nothing but 1 by k here, right? I am getting some finite value, it is finite. Okay, next, whenever the input is unit parabolic, so the acceleration error constant k is equal to limit s tending to s square into g of s. So limit s square, and this entire term is g of s, right? This is g of s. Okay, s will get cancelled. So yes, s is 0. So 0 into this. So I am getting the acceleration error constant ka is 0. Then find out the steady state error 1 by ka. 1 by ka is 0, right? Ka is 0. So 1 by 0 is infinity. So I am getting the steady state error as infinite. So I should not apply the unit parabolic input for the type 1 system because I am getting the steady state error as infinite. But I can apply the unit ramp input and I can apply the unit step input. For unit step input, the steady state error is 0. For unit ramp input, the steady state error is finite. But I can reduce this steady state error by increasing the value of k to some extent, right? So similarly, the same analysis for type 2, I will not just go through this, already I have told, right? The same analysis we will do with respect to type 2 system. What is type 2 system? N is equal to 2. So s power n. So s square. So I am getting this term s square in the denominator. So this is in standard time constant form. Time constant form. So if I calculate for unit step, I will not explain much here. For unit step, kp we are getting infinity. Kp is, because you know how to calculate kp, limit s tending g of s, the same thing you do it. Kp is equal to infinity will get. Then what about steady state error? 1 divided 1 plus kp. Kp is infinite. 1 by infinity is 0. So the steady state error in this case is 0. Yes, I can apply the unit step input because I am getting steady state error at 0. Fine, no problem. Then if it is unit ramp, the velocity error constant I am getting, how to find out, you know already, here it is there, right? I will not explain much. Kb is infinite. What about the steady state error I am getting here? It is 0. Yes, I can apply this ramp signal also because I am getting steady state error as 0. Is it fine? The next, whenever the input is unit parabolic, find out the acceleration error constant. It is k equal to k, some finite value I am getting. K is equal to k. It depends on system gain, and steady state error ESS is some finite value. Yes, I am getting some 1 by k, right? Okay, if it is finite value, you can observe here, I can apply all the kinds of inputs, whether it is unit step, unit ramp, unit parabolic, because whenever I apply unit step and unit ramp, the steady state error is 0. Whenever I apply unit parabolic, the steady state error is finite. It depends on the system gain k. If I increase the value of system gain k to some extent, the steady state error can be reduced, right? So all these analysis we should be knowing, and we will summarize this in the table for the summary of the steady state error and the types of control system, right? So along we will list out here. First one is unit step, second unit ramp, third one is unit parabolic, and here we will list out type 0 system, type 1 system, and type 2 system, and we will write down the steady state error. Steady state error means ESS I am writing. Already we have calculated ESS for type 0, type 1 here, right? So the same thing we are listing out here. So for unit step, for type 0 system, we got ESS is equal to 1 divided by 1 plus kp, right? And for if it is unit ramp, ESS is infinity, ESS is infinity for type 0 system. For type 1, the steady state error for unit step is 0. For unit ramp, it is some finite value 1 by kb, and for unit parabolic, it is infinity. For type 2, it is 0, 0, 1 by k, right? So how to remember this? You know the, just I will observe here, diagonal elements. These are diagonal. Observe here, this is diagonal, right? Right on the table. So you know the steady state error for type 0, 1 divided by 1 plus kp. This you will write, no problem. 1 by kv, 1 by ka. And above this diagonal, fill up zeros. 0, 0 and 0. Below this diagonal, fill up infinity, 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 infinity. I hope you can easily remember now, right? Along the diagonal, you write down the finite values of the steady state errors, what you got, right? Then above the diagonal, you will get 0, and below the diagonal, you will get infinity. And you know what is Kp, and what is Kv, what is Ka. This you have to remember, right? Okay. Okay, fine. Next, we'll proceed. You should remember this table. You should be knowing how to fill up the table, and so that it will help us to solve some numericals. Okay, for control system, we'll try to solve one or two numericals based on the error constants: position error constant, velocity error constant, and acceleration error, static error constants, right? So I am referring to static error. There are dynamic error constants also. We will not study that. Only we'll study the static error constant Kp, Kv, and Ka with respect to unit step input, unit ramp input, and unit parabolic input, and corresponding errors Kp, Kv, and Ka. Okay, example 4.22. For control system with open loop transfer functions given below, explain what type of input signal gives rise to a constant steady state error, right? Okay, and calculate their values. Means we want to find out steady state error and what is the corresponding type of inputs, whether it is unit step signal or unit ramp signal or unit parabolic signal, we have to tell and calculate their values. Means ESS also we have to calculate what is ESS and corresponding input signal. So we'll take one by one, and this table, you know how to do this table already I told. Okay, first let me take part A. G of S is equal to 20 divided by S plus 1 into S plus 4. Is there any, what type of system it is? Type 0 system, because S power n, here it is n is 0. So S power 0 is 1, here it is 1. So it is type 0 system. And for type 0 system, for unit step input, you can observe here, for type 0 system, observe this column here. For type 0 system, for unit step input, you are getting the steady state error as, for unit step, I'll write here one by one. For unit step signal, the steady state error is ESS, and it is equal to 1 divided by 1 plus Kp. For type 0 system, right? Okay. What is Kp? Find out that Kp. Kp is equal to limit S tending towards 0, G of S. So limit S tending towards 0. What is G of S? 20 divided by S plus 1. 20 divided by S plus 1 into S plus 4. Substitute value of S equal to 0. So I will be getting 20 divided by, this is S is 0. So 1 I am getting. So S is 0 here, I am getting 4. 4 1 ja, 4 5 ja. So I am getting 5. So substitute Kp equal to 5. So the steady state error is 1 divided by 1 plus Kp is 5. So substitute here 1 by 6. So 1 by 6, what is the, what I am getting 0.16, right? So 0.166 and so on. This is the steady state error, right? I hope you understood. Then what type of input signal it is? Unit step signal, and steady state error is 0.16. We have found out the steady state error, and we have calculated the value is found to be 0.16. And observe, for unit ramp it is infinity, for unit parabolic it is infinity. So no need to calculate, right, the steady state error for unit ramp signal and parabolic signal, because it is type 0 system, right? Next we will proceed with the part B. First we should identify what type of system it is, whether it is type 0 or type 1, type 2 and so on, right? Okay. So part B will take up G of S is equal to 10 into S plus 4 divided by S into S plus 1. Can anyone tell what type of system it is? Unmute yourself and tell. Don't put a message in the chat box. What type of system it is? Type 0, type 1 or type 2? I hope people are there in the class, then they are listening to my class. What type of system it is?
Type 1, sir.
Yes, good. Type 1 system, because observe here, S power 1, right? S power n. So it is type 1 system. Type 1 system. Okay, just observe the column here for type 1 system. So you can observe here, for unit step, suppose the input is unit step, the steady state error is 0. Suppose the input is unit ramp, then I am getting some finite value. We will try to find out, right? So the signal is unit ramp, and you will not consider the parabolic this also, because we are getting the steady state error as infinity. So we will take the only with finite value. We will try to find out those finite values. So unit ramp, let's see what type of signal it is. Unit ramp signal. And what is the steady state error? ESS for unit ramp signal, it is 1 by kV. 1 by kV. So 1 by kV. So how to find out kV? We know that kV is equal to limit s tending towards 0, s into g of s, s into g of s. So limit s tending towards 0. Okay, let me write it here. Let me go to the next slide. kV is equal to limit s tending towards 0, s into g of s. What is this g of s? Here 10 into s plus 4 divided by s into s plus 1 into s plus 2, s into s plus 1 into s plus 2. This is g of s. Is it fine? Okay, part B. Then ss will get cancelled. Substitute the limit s tending to substitute s equal to 0. So s is 0 here. 10 into 4, 40. I will get in the numerator, divided by s is 0 here. So I am getting 1 here. S is 0 here. So I am getting 2 here. So 2 2 is 4, 20 I am getting. kV is 20. So substitute kV value. So steady state error ESS is equal to 1 by kV. What is kV? It is 1 by 20. So 1 by 20 means how much? 1 divided by 20, it is 0.05 is the steady state error. So the steady state error, the finite value is 0.05, and the type of signal is unit ramp signal. We have found out, right? So what type of input signal we have found out, and steady state error and its value, right? Then we will take up part C. So here in our judging is very important, whether it is type 0 or type 1 or type 2. Once we identify type 0 or type, this table helps us what to find out, what not to find out, right? Okay. Then g of s will take up. G of s is equal to 20 divided by s square into s plus 1 into s plus 4. So type of system is type 2 system, because s is square, so n is 2, so it is type 2 system. Type 2 system. Just observe the table in the type 2 system here, this one, right? So if I apply unit step signal, the steady state error is 0. If I apply unit ramp signal, the steady state error is 0. But if I apply unit parabolic signal, the steady state error is some finite value, 1 by k. So we will apply the unit parabolic signal here. Unit parabolic signal. So what is steady state error for unit parabolic signal? It is 1 by ka. So how to find out ka? We know ka is equal to limit s tending towards 0, s square into g of s. So limit s tending towards 0, s square. What is g of s? G of s is 20 divided by s square into s plus 1 into s plus 4. So this s square will get cancelled. So ka is equal to, so substitute s equal to 0 here. 20 divided by, so s is 0 here, so I am getting 1. S is 0 here, I am getting 4. 4 1 4, 5 is 20. Alright, so substitute ka value here. So the steady state error is 1 by 5. What is 1 by 5? 1 divided by 5, it is 0.2. Right, so steady state error is 0.2. So we have found out the type of signal is unit parabolic and steady state error is 0.2. Right, so we have done this. We are done with this problem. Right, next we'll proceed with the next numerical. If any doubts, please unmute yourself and talk to me so that I can clarify your doubts immediately. Right, okay, next we'll proceed with the next numerical. A unity feedback system is characterized by the open loop transfer function g of s is equal to 1 divided by s into 0.5s plus 1 into 0.2s plus 1. Here what they are asking, determine the steady state errors. Means steady state errors means what? Kp, Kv and Ka. These are the steady state errors, right? So position error constant, velocity error constant, acceleration error constant, Kp, Kv, Ka. For unit step, for unit ramp and unit acceleration input corresponding. This is for unit step, This is for unit ramp, this is for unit parabolic. Parabolic means acceleration, right? Okay, fine. We'll find out the steady state errors. So g of s is given. So find out kp. You know what is kp? Limit s tending towards 0 into g of s. That's all. So limit s tending towards 0. What is g of s? Given. This is g of s is given. Substitute here 1 divided by s into 0.5 s plus 1 into 0.2 s plus 1. Okay, apply the limit s tending towards 0. So if I apply 0 here, anything divided by 0. So if this 0 means this entire denominator will become 0. So 1 by 0 I will get. What is 1 by 0? It is infinity, right? Is it fine? Okay, 1 by 0 is infinity. Means the position error constant kp is infinite. Then next we'll find out the velocity error constant kv. Is it fine? Okay. And whether they have asked to find out the steady state error, determine the steady state errors also they have asked. Not only steady state error means ess, error constant means kp kv k, means we have to find out the steady state error also. Okay, we'll find out steady state error with respect to kp. What I am getting, 1 divided by 1 plus kp. Just have a okay, 1 minute. Okay, we can observe here 1 by s. This is type 0 system, right? So type 0, this table you know it is 1 divided by 1 plus kb for unit step, right? For unit step. So 1 divided by 1 plus what is kp? Kp is infinite. So 1 by infinity. 1 by infinity is 0. So the steady state error is 0, right? Then next we will find out the velocity error constant and corresponding steady state error ESS, right? We have to find out this also. Then kv. So limit s tending towards 0, s into g of s. So limit s tending towards 0, s into g of s. What is g of s? 1 divided by s into 0.5 s plus 1 into 0.2 s plus 1. So ss will get cancelled. Substitute the limit s tending towards 0. So 1 divided by, so if this is s is 0 means I am getting 1. If this s is 0 means I am getting 1. 1 by 1 I am getting velocity error constant kv as 1. So what is the steady state error? It is 1 by kv. I know it. No need to refer the table, right? You should remember it. So 1 by kv, 1 by 1. So it is steady state error is 1 ESS, right? Okay, this is fine. The next last steady state error we'll find out with respect to acceleration, with respect to unit ramp input or unit acceleration input. So we'll find out ka, limit s tending towards 0, s square into g of s. So limit s tending towards 0, s square to g of s. What is g of s? 1 divided by s into 1 divided by s into 0.5 s plus 1, 0.5 s plus 1 into 0.2 s plus 1, 0.2 s plus 1. So s and this s square will get cancelled. Substitute s equal to 0. 0 into this entire thing I will get 0. Means ka is 0. I am getting ka equal to 0. Then what about the steady state error? It is 1 by ka. You know it, right? So 1 by ka. 1 by 0. Right? It is infinity. So we got the steady state error ESS as infinity. Right? You came to know. So we have found out the steady state error for unit step input, unit ramp input, and unit parabolic or input, also called as unit acceleration input. Right? Okay. The next, we'll move to the next topic. If any doubts, please unmute yourself and talk to me so that I can clarify your doubts. I'm repeating this, but nobody is asking doubt. If nobody is asking doubt, means everything is understood clearly. Or else you have to work and then ask the doubts. Then next, this is the last topic in this chapter, right? Dominant poles of transfer functions. What are dominant poles? I will tell you. So before, just I will draw the diagram so that you will clearly understand, right? So this is the S plane. S plane is a complex plane, sigma and j omega, right? Best the poles can be, this is left half of S plane, left half of S plane, left half, and this is right half of S plane. Left half of S plane is this one and right half of S plane RH, right? So this is imaginary axis. Towards left of imaginary axis we call it as left half of the S plane. Towards right side of the imaginary axis we call it as right half of the S plane, right? Okay, the roots can be, the roots or poles of the characteristic equation. The roots of the characteristic equation are nothing but the poles, right? The poles can be located on the left half of the S plane or right half of the S plane or imaginary axis. So these location of the poles will greatly affect the transient response of the system, right? Okay, the transient response means, you know, okay, just I will briefly tell you, already you know it. Every system has two types of response. C of t means it has the transient response Ct of t plus the steady state response Css of t, Css of t, right? Transient response as well as steady state response. Is it fine? Okay, but here, okay, let me take this x-axis is time axis and y-axis is the response of the system, and the input for the system is unit step input, that is 1.0, and the response of the second order system, let me take it, it is damped sinusoidal oscillator, right? Damped sinusoidal oscillations. Okay, then at time t equal to infinity the system will attain steady state, but before attaining the steady state, this we call it as transient response, right? This is Ct of t, transient response Ct of t, because the variations in the output before reaching the steady state, right? This is steady state Css of t from this part onwards, right? Is it fine? So these variations in the output before reaching the steady state we call it as transient response. Whether the pole is located on the left half of the S plane or right half of the S plane or near to the imaginary axis in the left half of S plane or far away from the imaginary axis in the left half of the S plane, that will decide the transient response, whether the transient response will last long or it is short. That we will to understand. Is it fine? Okay, that we will see. Okay, the location of poles is going to greatly affect the transient response. Just let me explain you this. Let me assume that the complex conjugate poles, for example minus 1, let me assume the poles are minus 1 plus or minus j, and another pole s equal to minus 10, for example. So let me locate these poles. S equal to minus 10 I will locate here. This is s equal to minus 10. This is the origin, right? I have located this pole. Then minus 1 plus or minus j. So minus 1 is here, minus 1 plus j. So I will locate the pole here, complex conjugate pole. This is plus j. Then here minus 1 minus j. We look at the pole here, complex conjugate pole, right? Minus j. So minus 1 plus j and minus 1 minus j. So you can observe here these complex conjugate poles that is located at minus 1 plus or minus j, they are near to the imaginary axis. They are near to the imaginary axis j omega, right? But observe the real part. The real part of this complex conjugate pole is minus 1, right? This is minus 1 and it is near to the imaginary axis. Observe another pole which is located at minus 10, which is far away from the imaginary axis as compared to this location of the first pair of poles, right? Suppose the location of the second pole, which if it is 5 times or 10 times, if here it is 10 times, because minus 1 is the real part, if I multiply by 10 it is minus 10 I am getting, means the pole is located 10 times far away from the first uh, first pair of poles, right? So if it is 5 times or 10 times, then we'll say that this is insignificant pole. This is not significant, which is not going to judge the behavior of the system. This is insignificant pole. Insignificant pole. Whereas this complex conjugate poles are the, we call it as dominant poles. Dominant poles, because they are going to judge the behavior of the system. Hence we call them as dominant poles. I hope you understood the difference between dominant poles and insignificant poles. The dominant poles are located near to the imaginary axis on the left half of the S plane, and the insignificant poles are located far away from the imaginary axis. I hope you came to know the dominant poles and insignificant poles, right? Okay, let me explain you with the example. I will take this example. This is the closed loop transfer function. M of s is equal to C of s by R of s, 20 divided by s plus 10 into s square plus 2s plus 2. You can observe here, this is not of the standard second order form, right? We know the standards. Let me write it. C of s by R of s is equal to omega n square divided by s square plus 2z omega ns plus omega n square. So this is the standard second order equation or form. This we know it. But observe here, we cannot compare because this is third order. If I multiply s plus 10 into s square, so I am getting s cube. So I cannot compare this closed loop transfer function with the standard second order system. So what to do? I have to, this is type 3 system, right? Sorry, s. The highest power of s is 3. This is third order system. Third order system. We don't know the behavior of third order, fourth order, fifth order systems and so on. We know the till second order system because we can compare and we can obtain the damping ratio as well as the undamped natural frequency omega n, right? So, but one thing we can observe here, let me solve the roots of this third order system, right? So, one set of root s equal to minus 10 and another set of roots. By solving this equation, I am getting s1 comma s2. So this is s1, s2 comma s3, s2 comma s3. The root is minus 1 plus or minus j. If I solve, after solving the roots of this equation, I am getting the roots as minus 1 plus or minus j, right? And already I have shown you the location of the poles here, minus 1 plus or minus j and minus 10. So minus 1 plus or minus j, we call it as dominant poles because they are located near to the imaginary axis. I am stressing once again, right? And minus 10 is located far away from the imaginary axis, hence these are insignificant pole. If it is insignificant pole means I can neglect this term, I can neglect this s plus 10 because it is not anyhow going to judge the behavior of the system. So if s plus 10 is not there means it is as good as I am analyzing, I am reducing this third order system to second order system and I know the behavior of the second order system, right? So I can compare this s square plus 2s plus 2 with this standard second order system and find out the value of z and omega n, z and omega n, right? So if I find out the value of z, it turns out to be 0.707 here. You know how to find out, I am not telling you, right? 0.707. Compare because omega n square equal to 2, 2z omega n equal to 2, right? Find out the value of omega z equal to 0.707. And this z of 0.707 we call it as the relative damping ratio. Why? Not simply damping ratio. Why we call it as the relative damping ratio? Because we are judging the damping ratio of the system or damping factor of the system by reducing the third order system to second order system. Hence we call it as the relative damping ratio. I hope you got it. And you came to know the significance of dominant poles and insignificant poles. The dominant poles are going to judge the behavior of the system. If it is third order system here, in the case of this example, whatever I have taken, s plus 10, s equal to minus 10 is the insignificant pole, I can neglect it. And these complex conjugate poles, minus 1 plus or minus j, these are dominant poles, they are going to judge the behavior of the system, right? So if z is 0.707 means, what is the meaning of that? Z is lying between 0 to 1, hence the given system is underdamped system. And you know the nature of underdamped system already we have studied, right? So we'll stop our study here, okay? If any doubts are there, you can unmute yourself and talk to me. So I'll stop recording.